Up next, we have Tim, and he's from Temporal. The guy no more intro. Give him a round of applause.
All right, so I'm here to talk says reliability, but specifically I'm going to talk about handling overload, partially because that's what I've been interested in lately. So if you hope for other bits of reliability, I'm sorry, you're welcome to have your own talk, though. My name is Tim Deeb-Swihart. I'm a software engineer at a company called Temporal. We do durable execution. This is not a talk about them, so that's all I'm going to say, except to talk about some production incidents we have that demonstrate useful points. I'm a systems weeb and reliability nut. I read papers in my free time. This is just fun for me. Background, blah, 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 blah. So high level, we're going to talk about what load is, what overload looks like. Overload is a feedback loop, which is part of why it can be so bad to deal with in production. Various defense mechanisms, including some that seem to be regularly reinvented but forgotten despite being there on your computer since like the 80s, which will be kind of fun. And then a bunch of resources to learn more because there's lots of papers, blog posts, books from Google that are useful on this topic. So we're going to start off with what is load. So load is demand placed on a system. These are RPC calls. They're HTTP requests. They are database queries. They are like background compaction in your log structured merge tree, garbage collection. Every bit of load, every bit of work in your system will consume resources, memory, CPU time, network bandwidth, disk bandwidth, etc. And those are all limited quantities. And and overload is what happens when demand exceeds capacity. This is pretty simple. One thing that people often forget or don't know is that as load increases, contention will increase latency. And this starts to lead to bad situations. So let's say we have a service, the single CPU, that can handle 100 requests a second. If requests are arriving at some rate less than 100 RPS, you're totally fine. Everything's handled. You're getting 10 millisecond latency. Your customers are happy. Your on-call engineers are happy. But then they start to arrive at 101 requests per second. After a second of time, only 100 of those could have been completed. So you now have 2 requests processing at once. Latency is now 20 milliseconds. As this continues, latency will compound and worsen until your system probably falls over. It's not actually literally going to catch fire, but metaphorically speaking, it's going to page your on-call engineer and they might catch fire. So eventually, the service will be so overcome with load that it can't actually function. It's spending all its time, swapping context between threads, hitting locks in your process, etc. There are a lot of things that can lead to this, like memory leaks. If you've got a memory leak in your program, it increases the time spent on garbage collection, which decreases the time you get on the CPU to do useful things, which increases request latency, which can cause timeouts in upstream systems, which can cause et cetera, et cetera. There's a bunch of ways. CPU exhaustion, seasonal variation in workloads. Like it's Taco Tuesday, and you have 10 times the number of requests as normal, and you didn't scale to handle that, and suddenly your latency's through the roof. Performance regressions is a common one people forget. You roll out a version that can handle 5% less than it could previously, and you don't catch that, and it's Taco Tuesday. And it falls over when you should have been scaled up to handle it otherwise. So in general, higher load leads to more contention, which leads to higher latency, timeouts, and eventually, if it's bad enough, collapse, or like congestion collapse, if you want to think of it in TCP. Specifically later, we're going to talk about retry storms and load amplification, because this is an example of a feedback loop, of a gray failure or a metastable failure if you follow like the academic literature in this space. So a very simple example, let's start with, this is a very basic system design, is a look-aside cache. Request comes in, you check the cache. If it's not in the cache, you check your database, you get the result, you put in your cache, all is happy. Because caches are fast, everything's usually in memory. You're using, let's say, Redis or Memcache. Your database has to hit disk. It's got a query planner, blah, 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 blah. You can often serve multiple times as much load with a cache as you can with a database. And let's say you've got a cache hit rate of 90%. 90% of your requests go to your cache. You can now handle 10 times as much load without paying for more database space until your cache crashes. Because when your cache crashes, all of that load goes to your database, which is now handling 10 times as much load as it could beforehand. And the worst thing about a situation like this is your database is handling so much load, you can't refill your cache to take load off the database. You've entered into a feedback loop. You are stuck here until something comes in and jolts the system from the outside out of this state. this is the worst part about overload, is that in many cases, an overloaded system will continue to overload itself, and you must take drastic measures to pull that load off. Sometimes adding a lot more servers, sometimes restarting things, sometimes actually cutting off load from the outside world. We're going to talk next about a self-induced feedback loop, and that's a retry storm. So this is a very simple, another simple service. You've got client, service, database. Requests go left to right. All is happy in the world. Let's say it's handling 100 queries per second because small numbers are easy to talk about in a talk like this. The database is all nice and happy, and let's say it spikes up to 105 queries per second. You start to see timeouts from your service to the database because it's now handling, like we mentioned earlier, 5 extra queries per second that it can handle. The problem with timeouts is, let's say your service is smart, your client is smart. You retry requests twice after they fail. So it times out and you retry it. And then something else times out and you retry it. And then the client sees a timeout and you retry. And if you were retrying twice for every request failure, you end up getting a 9 times workload amplification because of this. Each layer triples the amount of load going into the system. You know, client, the service to the database, 3 times the load. Client to the service, 3 times the load. If your retries are retried, you start to punish and basically light your database on fire. This is extremely common. I've seen it in production at multiple companies. Peers have seen it in production at multiple companies. It is extremely easy to write this feedback loop yourself and only find out at like 3 in the morning when you want to be sleeping instead. So fundamentally, there's a fixed amount of work that a system can do in a point in time. There's some bottleneck, whether it's CPU, it's memory, it's threads, and our goal is to figure out what that limit is without actually having to find that limit in production. Anything over that limit will cause queuing, increased latency, and eventually overload. So we're going to start with some terminology and then go through kind of a couple of mechanisms for handling this. We're going to go from limiting work in flight, talk about limiting concurrency, breaking feedback loops when you are in an overloaded state, retrying failed requests and how to do so without amplifying load like we've talked about, testing, obviously one of the most important things you should be doing, and then some complications of open questions that I'm not going to bother talking about, but I'd be happy to talk about after the presentation. And there's a bunch of other obvious things I'm not going to cover. This is just what I found interesting for a talk. Like, you should add timeouts on your requests. You really should. You should propagate cancellation from service to service. They're not in the slides. You should be doing them anyways, however, or should get to doing them. So the offered throughput of a system is the amount of demand placed on it. That is the 105 queries per second earlier that are blasting that database. The good put is the amount of actual useful work that gets done. And this is useful work not in terms of it's consuming resources, but useful work in that it successfully completes what you set out to do in, say, under your SLA. These are not errors. These are not SLA violations. These are things your customers are happy to be paying you for. Our goal is to maximize good put in an overloaded situation, because you will be overloaded, but you can actually maintain high levels of good put, or at least good latency for some subset of your requests despite that. The final term is back pressure. And you'll hear this some places, but you can think of it as friction. It is resistance to the flow of data through your system. This can either be implicit, so say like blocking a request until there are tokens available in your rate limiter or in a semaphore, or explicit, like you get HTTP 429 too many requests, or whatever the hell the gRPC equivalent is. So this is the slight rant slide. I hate rate limits. They are great for quota management. They're fragile when used for system protection, and they're unfortunately the very first thing people jump to. You look at your charts and say, we're healthy serving 7,000 queries per second in our database. You stick that in a rate limiter, and 3 months later it pages you because that still wasn't good enough. The problem with rate limits is that they are corrected about one time and one time only, and that is when you measure them. Because any change in the system invalidates that number. It could be a performance regression. It could be, you have 7,000 queries, but you measured it with like, I'm doing a select from a table with 10 rows, and in production, your customer's like, I'm going to select from that table with 1,000,000 rows. Those queries are drastically different in terms of the amount of load, the amount of actual work that has to be done, but they're treated the same by something like this. They don't adapt. Netflix had a great blog post on this from, I think, 2018, where they figured out these same things, that rate limits suck for protection. However, they are great for quota management. Like AWS has service quotas. This is kind of a billing and capacity management concept, or a capacity planning concept, where like Temporal charges like actions per second, which is some subset of our API. That shouldn't be used for system protection. That's wholly for capacity planning and budgeting. I'm going to stop ranting there. Unless you have like perfect predictive scaling, this isn't going to work. Even then, it probably won't work. So I want to talk about something that seemingly gets rediscovered every 6 years ago that hasn't stuck, unless you work specifically in networking, and you might already have an idea in mind. But the idea is that we shouldn't restrict how much work is done over a chunk of time, but how much work is done concurrently. Because fundamentally, it is that resource sharing that is increasing latency and causing contention. More concurrent work, more contention, higher latency above some healthy threshold, etc. And ideally, we want a system that requires no work to configure, will adapt to changing, so I'm not reading the bullet points, so pardon me, adapts without having like centralized coordination, because that won't scale in a high load system, will adapt to changes in topology without having to be informed, and is pretty easy to compute and enforce. If you care about theory, there's a kind of an observation from queuing theory called Little's Law, which states that the long-term number of requests in a system is equal to the long-term average arrival rate, that is the rate at which requests arrive, times the long-term average of the amount of time a request spends in the system. What matters there is we don't control really how long a request spends in the system. That's a function of the amount of, of your business logic. It's the function of like waiting on a disk sequence NVMe, but like you're waiting for a disk read, you're waiting on a mutex or something. We can control the number of concurrent requests in flight and use that as a proxy for latency, because at a certain level or above a certain level, latency will increase due to sharing. So we should be able to learn what that limit is without having to manually tune it. And so we're gonna take it, so if you know networking, this has been done since like the 80s in TCP. So if you've ever looked at a trace of like the send rate of a TCP stream over time, you'll see exactly what I'm talking about. You'll see initial load, it goes up, like cubic growth, whatever the hell it is. Packet loss happens, it drops down. Goes back up, packet loss happens, drop back down. And what you see is this sawtooth behavior as it seeks the correct number of bytes. Or the maximum number of bytes it can send concurrently without causing packet drops. This is what most congestion control algorithms do. Things like Vegas or BBR are actually doing it based on changes in measured latency, which is a cool way of doing it. It pushes you at a different end of the overload spectrum in a much more healthy spot, in my opinion, but we're not going to get into that too much here. But this is something that's been done in your computer and is done constantly that pretty much none of the distributed systems you work with will do. They'll have like manually configured concurrency limits. They'll have manually configured rate limits. My product has all of that. I'm trying to change it, but it has all of that right now. But we can learn the same way. One way is that if you track service latency or track the latency of the whatever call you're trying to limit, you can actually look at changes in latency over time to identify when you're putting too much load on a downstream system. So like if you have a long-term moving average and a short-term windowed average, if you're above the long-term average, you're probably sending too much load, you should back off. If you're below it or at it, you should add load because you're not yet at the maximum throughput you can have. This is a picture from Netflix's blog post, Performance Under Load, where they rediscovered this in 2018. If you search for this over the years, you'll see like posts from like 2013 and 2008. But it's basically nowhere, which sucks because we're all stuck in kind of the dark ages of handling overload from this perspective. The cool thing about this is it learns. Much like TCP, this is uncoordinated. And this works on either the server side or the client side. Like TCP, if it's in your clients, you don't control the server, you can protect, say, an external database or an external API that you don't use without having to care about any of it. If you up your rate limit from them in your quotas, it'll just learn, it'll adapt. You don't have to do any manual work to adjust. And it'll work server side too if you don't control your clients. So you can protect yourself so long as your clients respect your back pressure. If you send HTTP 429, they go, no, give me what I want, you just gotta block them at some point. But once you have some control over how much work is in flight, you need to start thinking about what do you do about the excess, because that has to go somewhere. So load shedding is one of the first things to think about in terms of breaking that feedback loop. This is essentially dropping ACKs. This is taking that excess load and just putting it in the bin. You say, I'm just not going to handle this. Here's your 429. Here's your gRPC status 8 resource exhausted. I'm just not going to deal with it. The image here is from a blog post from the Amazon Builders Library or the AWS Builders Library. I highly recommend you read it if you are a distributed systems person. It is fantastic writing that covers a lot of very practical system design things. I've got links to it later. I think they'll share these slides. Wholeheartedly recommend it. But this shows that graph from earlier about goodput versus throughput, but with and without load shedding. With load shedding, you can actually see that goodput remains high until the cost of rejecting requests actually begins to dominate CPU time, which will happen. But if rejecting a request is cheaper than actually doing the work, you can get away with, as you can see, like almost a tripling of load before actually having a collapse. So this is cool. This is all still server-side or like in your clients. But it requires work on your server to reject these requests. So let's talk about client-side mechanisms you can use to stop load from getting there in the first place and further help break that loop. The most traditional is a circuit breaker. Just like a real circuit breaker, it trips at a certain point, it resets at a certain point. I can walk through the state machine. It's a simple state machine. It's okay. Like most people have seen a circuit breaker, or you can find them easy. The idea is that you monitor, say, the error rate over time. If it hits a certain threshold, you stop requests. After a certain amount of time, this is your back off basically, given for the downstream service to recover. You open the circuit breaker or half open it to probe and allow work to continue. Some examples, Resilience4j. This kind of replaced Netflix's Hystrix or Hystrix project, if you've ever seen it. Open source. There's GoBreaker if you use Go. I didn't look for other languages. They will be out there though. But I want to talk about another adaptive method. Because we can actually, if we're modeling and tracking the failure rate over time, rather than fully stopping and then slowly reopening, or like fully stopping or completely opening, we can start to taper down the load based on the failure rate. And the idea is that if, say, 10% of recent requests have failed, and these are failed not for like, it's an invalid request, or your key is not found, but failed for like, hey, resource is exhausted, try again later. That you can reject requests with probability proportional to that rate and be able to get higher overall goodput than if you fully shut down traffic all the time. This example is from Google's SRE book. I'm not going to walk through it. This is basically, K is just a scalar, but if 10% of requests have failed over the last window, reject 10% of new requests locally. Done. You've reduced load on the downstream system until it has time to recover. Once all your requests are healthy again, you start throwing all of your load back at it and all is just fine. Pardon me, my computer threw up something irritating. So we've talked a lot about rejecting requests and what to do when you are overloaded, but let's talk about how to retry, specifically so you don't have that retry storm, that explosion we talked about earlier. Come on. This is easy. You just use exponential backup with jitter. I don't have anything else to say. This is just kind of what you use. This link is to some analysis from AWS where they looked at a number of back-off algorithms over time. They compared the number of calls over time as well as the actual wall clock time it took to complete the amount of workload. Just use exponential backup. I'm not going to waste your time saying anything else. It's great. It's easy to write. You don't have to think any more than that, frankly. But there's another thing that I've seen a lot less of that helps taper down the amplification we talked about earlier, and those are retry budgets. So the idea is to prevent combinatorial retry explosion. Like we talked about earlier, this is our service from earlier, just transposed so it fit on the slide. We've got a 9x explosion here. Client to service, 2 retries, so 3 times the load. Service to database, 3 times 3 is 9. The idea of a retry budget is to limit the amount of overall work in flight that can be retries at any point in time. This is something like I'm service A, and only 10% of my work in flight can be retries at any time. If I need to retry a request and I have 10% in flight, tough luck, throw it back to the client. And this doesn't mean the client doesn't retry it, but it means that A stops amplifying retries after 10%. And you end up, in this case, with about 1.21 times growth in terms of load instead of the 9x. And it's 1.1 is the 10% chance squared. So 1.21 is far less than 9. Your servers, your services, your on-call engineers, if it's not you, will thank you. And if it is you, you will also thank you. Testing. If you've not load tested your system, it will fail in the worst way possible. You can just assume it's going to fail in the least convenient way at the least convenient time because you have no confidence in how it will behave. And if you are doing load testing, you shouldn't just go to where it breaks. You need to go well beyond and then stop, back off to and let it recover and see whether it can recover. Because if you get something like the retry storm we talked about earlier, it's not going to recover. And that's a failure in the design or just a hole in the design you need to patch. Testing is going to show you as well where your bottlenecks are, like where amplification is happening, where you are spending excess time that is causing overload. Like, we've got a hot allocation here, and now 30% of our CPU time is spent on garbage collection. It's a real thing we fixed recently. It's awful. Load test your things before production. Your customers load test them for you. There's some other things about testing both in isolation and concert. Basic testing guidance applies. If you test things in isolation, you can find where their bottlenecks are. If you test in concert, you get to see all the weird, funky interactions because things never interact exactly as you anticipate, unless you formally prove them. But, very few of us do that, unfortunately. And there's a lot more complications that can go on here. I didn't get into these. I didn't think I had time. I'm going a little bit faster than when I practice, but that's fine. Fairness is kind of like the real world. Like in a multi-tenant system, let's say your database is serving traffic for internal services. Who do you limit first? If you're limiting randomly, you can get into a state where, say, you've thrown out 80% of the traffic for one of your customers, and another customer is all their traffic going through just fine. If that customer you're rate limiting is the customer who pays you the most money, that sucks. They're not going to be happy with you. No customer would be happy with that treatment. So there are ways of, didn't put them here, happy to talk about them later, but you have to think about how do you limit in a way that is fair with respect to all of the things that depend upon you. Prioritization as well. If you just throw requests out randomly, congrats, you could be throwing out all of your critical requests to allow things like health checks to get through, are you alive? But you're not doing any useful work. It's just like, ping, are you there? Ping, are you there? And that's not a useful use of your time. So you need to think about what do you reject first in terms of what load is critical to your functionality and what load is sheddable. We would like to have this, but if we don't have a choice, just throw it in the bin where it belongs. As well as heterogeneous requests. So many of the methods like rate limiting, even the adaptive one I talked about earlier, assume that requests are homogeneous. That is, they require or put the same amount of work on the system as each other. This is, say, a select 10 versus a select 1 million. Those are vastly different amounts of work that are treated the same by most paradigms like this. And you may find you don't actually need to care. In a lot of real-world systems, you actually don't need to care. It's good enough. And that's enough of an edge case that statistically speaking, you're unlikely enough to be a problem. But if it is, you have to think about it. There was a talk from Tony Allen at Lyft who added adaptive concurrency control to the Envoy service mesh. And one of the things they talked about is, if this is your problem, like you are a database or have heterogeneous request loads, congrats, that's an open problem. I feel for you, it's not covered in this talk. I've got cool ideas on it, happy to talk later, but like there isn't like an open, like, hey, here's how you should do it. You have to think about how to model that yourself. Like all your textbooks say, these are left as an exercise for the reader. Yeah, so I am a little bit early. Does anyone have questions? I have a slide of resources, but any questions? Thank you.